SRAM lecture is the FinFET based SRAM. First name, let's discuss what is FinFET. This is for today's mainstream technology now. But historically, the transistor, is a traditional so-called planar transistor, 2D transistor. And this is a traditional planar transistor, and we draw the source here and the drain is on the back side, and this is a gate. So in this geometry here, the W is here, and then the L is here. So this is planar transistor. And the FinFET is to make it non-planar, like 3D structure. So we create this fin, very thin fin. It's like a wall here. And then the gate is surrounding the fin. So it's like this. If this is a fin, this is silicon, and your gate is surrounding the fin like this. And the reason, as we discussed before, this is to deal with the short channel effect, because ideally the transistor should be a gate control device, and the method to increase the gate control is to increase the coupling between the gate to the channel. And if it's planar transistor, gate only covers the top, so then the gate to channel coupling is not that strong. And if you do this FinFET structure, then if two sides, the channel, are coupled to the gate, so the gate has more coupling to the channel, and then it will be better short channel effect, purely due to the electrostatics. And this is called FinFET because it's like the fin of the fish. So in this FinFET, then my question is, okay, of course this is still your L, but my question is, what is the W in this case? What is the W in this FinFET? It's written there. So because you look at the gate to the channel, so this is the contact area between the gate to the channel. So you have two sides of this fin. That means 2 times the height of the fin, this H fin. And then the top, in many cases we have this tri-gate, 3-side gate. So then top is also in contact. Then the let's say the thickness of the fin is also in this W. So now the W becomes this. Okay. This is the W over L, that W. Or sometimes we call this is the electrical W. This because electrically the current will flow proportional to the W. Okay, so any questions?
So the depletion depth is greater than what the thickness of the fin is?
Yes, almost fully depleted. Yeah. So this concept of FinFET was first invented by Professor Cheng-Min Hu's team at UC Berkeley in the 1990s. And this is the first demonstration of the FinFET at 1998. This is a MOS, N-channel device. And this was fabricated in the Berkeley's university clean room. And this paper was reported in the IEDM, which is the top device conference in this community. And this is the schematic of the design, and this is the experimental data of the IDVG and the IDVD, those two kinds of IV characteristics. And here are the dimensions, like gate length, like 30 nanometer, and the fin width, 20 nanometer, and fin height, 50 nanometer. So this was, amazing at, this is how many, more than 20 years ago, at the university, a clean room, and makes such small devices and show almost perfect IDVG curve. So the substrate slope is pretty good. And then, so this was the first demonstration of the concept. And 1 year later, the same group demonstrated the p-channel PMOS FinFET. And again, this is the dimensions and the IDVG and IDVD curve. So this since this 1998 or 1999, the concept was proven by university lab, and then a lot of research started working on this FinFET from the academia and the industry. But it took like 14 years for the industry to really commercialize this technology. This is 2012. Intel first announced this FinFET design at 22 nanometer technology node, and of course Intel called it Tri-Gate, probably to avoid the patent issue, whatever. And so they call it Tri-Gate. But essentially, it's this FinFET concept. And here are some images for the Intel's 22 nanometer transistor. And here, this is the like bird eye view for this. And then we have multiple fins. And then this is the gate. And this is the source and drain. So if you cut this along, let's say, this direction, then you will have this cross-sectional image here, and from this you can basically you are seeing like this cross-section. So here there are some dimensions of interest, and here we see the height is 34 nanometer, and the width on average is like 8 nanometer. So if I ask you what is W, then you can calculate by yourself. Okay. And then if you cut this along the other direction here, then you get this figure. So this is from source to drain, and this is a gate, and this is a contact gate pitch as we discussed from source to drain here, and this is 19 nanometer CGP. And this is another view, which is you are looking at exactly this surface, and you have gate surrounding like this. So, and this is the IDVG curve for both NMOS and PMOS, and it has pretty good like subthreshold slope, that's like around 70 millivolt per decade, and we know the best you can do is 60 millivolt per decade. And compared to the initial design from Berkeley, so the differences here are the tri-gate instead of double gate. Originally, only the two sides are the gate, but here the top side is also the gate. And also here, Intel used the bulk silicon instead of SOI, silicon-on insulator. This is due to the cost reason. So the bulk silicon process is cheaper. And Intel used this high-k metal gate with the gate last process. And I don't think we have time to discuss what is gate first and gate last process. But this is high-k metal gate. And then I just want to talk about the differences. Let's say for a circuit designer, if you're not a device engineer, then for circuit designers, what do you need to pay attention to if you are designing the circuit with FinFET instead of planar transistor? So the biggest change here is the W now is quantized. Why is that? Any idea? So you look at this layout between, let's say, a conventional planar bulk transistor, and this is your, let's say, this is your W, right? You can define the W as you wish. Right? As a circuit designer, you can define the W as you wish for the conventional bulk transistor, planar transistor. And your W over L can be 1, 1.2, 1.5, 1.8. But for the FinFET layout, you look at the W. It's quantized because here you can only have integer of those fins, right? You cannot have 1.5 fin. What does that mean? So the integer nature of the fin gives the quantized W. And the W here effective, as we discussed, each fin will give you this 2 times h of the fin plus the t of the fin. So that is the electrical or effective W given by each fin. And then you can tune the number of fin. So for example, in the Intel's case, we can do this. So the W here, 2 times 34 plus 8 is 76, right? So then that means here this W can only be 76 nanometer times 1 or 2 or 3. You cannot have any other values in the circuit. So that will cause some limitations in the design. So this is the electrical W. But however, if you look at the physical footprint, there's another W you want to pay attention to. So this W is the actual physical, let's say, fin-to-fin pitch. So this P fin is the pitch from one fin to another fin. This pitch is different from this electrical W, right? Because electrically W is this one, but the physically it only takes this space. So you need to pay attention to those two different W. One is the W for the electrical current to conduct, which is the surface of this fin, and then the second W is the actual width, physical width of the fin on this 2D dimension.
Are you assuming that the doping area or the doped volume is then only confined to the fin? So let's say if you dope the fin on the other side, it's only within that fin that it's got the source and drain doping. It's not.
So here the doping, yeah, that's a good question. We will give to say this actually. So typically for the FinFET, the channel is undoped. You don't dope anything because it's so thin, and you can, because now the gate has better control, you can tune the gate work function to tune the threshold voltage. So you don't dope the channel. And for the drain, drain source and the drain is no longer that thin. So we have the extension area for the source and the drain, so we can dope that area. But for the fin itself, it's typically undoped. And because of this, so you don't have the RDF, this random dopant fluctuation in the channel, so then reduced variability. And this is one advantage. And also, of course, you improve the SS and reduce the debol. Those are the non-short channel effects. Of course, with the FinFET, better electrostatic control, then you improve that. So as a result, you look at the butterfly curve of the SRAM. This is a planar transistor design. This is the FinFET design as a same node. Then you can see that this is larger than the conventional design. So this is the benefit of the SRAM and based on the FinFET. Of course, the problem here, the cons, as we already discussed, the W is quantized. You don't have that flexibility to tune the W as you wish. And secondly, as we discussed, because the doping is not available, then the threshold voltage engineering can only be done by the gate material, like the metal gate work function engineering. Previously, when you tune the threshold voltage of your planar transistor, what you can do is just change the doping level of your channel. Then you can change the threshold voltage. So here, this is just another comparison between the planar FET and FinFET, and this is the layout. So here, the planar transistor, you can change this is pull down transistor. You can change the width. And here you can only have, let's say, 2 fin for the pull down. You cannot have 1.5. So similarly, as you increase the fin number for the pull down, then you can effectively you increase the beta ratio of the transistor SRAM cell. So you can improve the read margin. So this is similar as planar transistor. And here are some interesting photos from the Intel 22nm tri-gate SRAM family. Because as we discussed, for the SRAM cell, you may have different applications like L1, L2, L3 cache. So you may size the SRAM differently in terms of the pull down to pass gate to pull up ratios. And here, Intel offers 3 kinds of SRAM cell at 22nm load. And this is the image, let's say this microscope image of the layout. And my question for you is, what is the pull down, let's say this ratio, pull down with pass gate with pull up. So if I give this kind of image to you, then you need to figure out what is the ratio here. Any idea? For example, the first one. So where is the pull down? Again, that question. Where is the pass gate? So because this is very regular layout, so in the middle is the PMOS region, and it's pull up. This is pull up, and then this is the pull down, and this is the pass gate. I mean, this is pass gate. Sorry, I should draw this way. This is the pull up, this is pull down, and this is the pass gate. And all of them will have only one fin. As you see, if you pay attention, here is just one fin. So here the ratio is just 1:1:1. And then you can do the others by yourself. For example, the second one, the pull down, here 2, and the pass gate 1, and then pull up 1. So you can figure out this out by yourself. I will skip the rest. So look at how many fins there.
Sorry, the gates are running vertically in that picture.
The gate?
Gate is running in vertical direction.
No. This is the gate. This is a fin. So this is a gate.
Okay.
And this vertical, this is a fin.
Okay.
The gate is wrapping around the fin. So here you can see that by this different sizing, and then you can improve the, let's say, the Schumann plot. This is again the supply voltage versus frequency, clock frequency, and this is pass and fail. And by scaling and by doing those sizing, you can push either higher frequency or lower supply voltage from generation to generation. So this is the benefits of the scaling. And I think two more slides. So in 2014, Intel introduced the 14nm tri-gate technology. If you compare the 14 versus 22nm, the difference is that this fin is even thinner, and the aspect ratio is even larger. So that's a key difference between the 14 and 22 nanometer. And in 2016, Samsung first reported 10 nanometer FinFET array for like 128 megabit SRAM array at 10 nanometer in this IFCC paper. And it also offered two kinds of cells, different ratios for either high density or high current. High current means faster, high speed. Okay, so to summarize the SRAM section, so SRAM comes free with CMOS logic process. They are the same kind of fabrication process, but there are special design rules to enable a very dense layout of the SRAM cell. And the parameter variations is a key challenge for SRAM design at the advanced technology node. And soft error will also become worse when you scale. And that's why we have to combine the circuit and device techniques to improve the cell stability. From the device side, of course, the FinFET technology. And from the circuit side, you have read the homework papers, right? You have different techniques. And the FinFET-based SRAM nowadays is a mainstream technology. So I think that's all for the SRAM lecture. Any other questions?